Now we are live. Hello, everyone. Today we have lecture with Mohammad about edge computing and how it can be green. In terms of power consumption. Okay, Mohammad, please give us some summary, some background of yourself.
Yeah,
Yeah, thank you.
yeah. Hi, Neda, and hi everyone. Thank you for inviting me. Maybe I can start sharing the slides because I have an introduction and a background on my research as well as this presentation.
Yeah.
Uh, mm,
I think I add to a stream. Now we have your lecture.
yeah, good. Thank you. All right. So the slides are shared now. Yeah.
Yeah, and please
Yeah.
introduce yourself.
Okay. Thank you.
Welcome.
So in this presentation, I would uh, present this edge computing for the Internet of Things when we include energy efficiency and serverless computing. I'm Mohammad Sadiq Asrampur. If I want to introduce myself, I would start uh, with some uh, a summary of this research I have done recently after joining Monash University, Australia, and also CSIRO, the research organization in Australia, particularly the Data 61 group. Uh, I am doing some research on cloud edge and serverless computing, and particularly doing some resource management in this area. And recently, I've been interested in uh, resource management for energy efficiency. Uh, but we know that this energy efficiency is not the only challenge for this area of study, but it's very demanding area to work on.
Yeah.
Uh, I have some experience on uh, working in industry as a software engineer and also teaching and doing some review for journals and conferences. And also, I have some hands-on experience with some cloud services provided by Amazon and Oracle, and also some tools and technologies when we deal with resource management in cloud computing, also in edge computing. Tools like Kubernetes, Linux, Docker, Ansible, and so on. And also, during the recent years, I have been lucky to receive some scholarships and funding from Monash University, CSIRO, and also recently a couple of scholarship from Building CRC, which is a research group in Monash University, Queensland University, and some other universities in Australia working on smart building technologies. Uh, in this presentation, I would cover the following topics. We start with Internet of Things to get some idea of what we mean by Internet of Things. Then we introduce edge computing because we believe edge computing can handle some problems of Internet of Things. Then we get a bit focused on the green computing or energy matters in edge computing. And then we think that serverless computing can bring some addition to these technologies. We introduced serverless computing, and uh, we also highlight the point that serverless computing can uh, be involved in edge computing, although it's originally designed for cloud computing. And understanding all these topics and having an introduction on all these topics, we at the end try to solve a sample problem to see how in research we deal with the problems in a real world. That might be helpful for people who want to uh, better understand how we define a research problem in edge computing and how we solve the problem. All right, let's get started with the Internet of Things. We all know that IoT devices are everywhere around us and they are increasing very fast. And we are not limited in just particular use cases. IoT is everywhere, like smart homes, wearable devices, smart cities, smart grids, industrial internet, and so on. Uh, for example, when we say smart cars, we mean cars that are equipped with a computation capability and they can communicate with the area around them, they can communicate within infrastructure, they can communicate with each other, and so on. And this is how they are made smart. In terms of smart city, I just want to give you some examples of smart things that we call them Internet of Things. Smart
Yeah.
city is another one. We uh, we know many of use cases in smart city that some people have done some study to see which ones are more important. And you can see that connected public transport and traffic monitoring are of the most important ones. But there are lots of other use cases in smart city that can be very important as well. Maybe a smart, just there is something in this uploaded file, there was some animations in the slides. Now that I have uploaded the file, I can see that it's just like a picture, not an animation. Maybe I can share my screen instead of using the uploaded file to show the animations. Would that be okay?
Yeah. Uh, of course you can.
Yeah.
Uh, just I should stop the sharing here.
Yeah.
Mm,
Perhaps we could call to remove from stream.
y- yeah, you can share your screen.
Let me share my screen.
Yeah, at the uh, bottom on the share, there
Yeah,
yeah there is an option for sharing a screen.
yeah.
Yeah.
Is it shared now?
Yes. Internet of
Good.
Things. Uh,
Smart city. Yeah, good. Thank you. Yeah, this one will be better.
yeah.
Right, so we have smart city as another realization of Internet of Things that we can see that there are many use cases inside smart city to be handled by Internet of Things. We also have smart farms or smart agriculture. That this one has also many use cases. Just want to give you a traditional way of handling the problems in smart farming. See, I hope the voice was also shared. This mechanism was to deter the birds from the farm because uh, birds are just damaging the crops in a farm, and we needed a mechanism to deter birds from the farm so we could improve the uh, crop, right? This is a traditional way of handling this problem in a farm, but now with the Internet of Things, we instead are using some fake hours through the farm. These fake hours are IoT devices like this,
Mhm.
and in fact, they are like a computer. If you disassemble them, you can see that there is a tiny computer inside them. This computer is a single board computer called Raspberry Pi.
Yes.
Uh, that is connected to some sensors in this fake owl, like a camera and sensor and things like that. And it
Mhm.
is monitoring the area around the fake owl. And if it finds a bird, for example, it starts making a noise and moving so birds leave the area and don't damage the farm. So this is one way of realizing the Internet of Things in smart farming. Smart building is another use case that I just want to give an introduction on. I just want to see how the Internet of Things is observed around us in different use cases, right? This is a construction site where different people and different machines are trying to uh, finish the task of this building, right? Using Internet of Things, we can, for example, enable a surveillance system to monitor the devices. For example, the yellow area you can see, this is a hazard identification. The camera is trying to monitor the area, and in case the machines and workers will be in a hazardous situation, then the application will, for example, give a warning or make a noise or something like that. Another application will
Uh,
be the word. Yeah,
Mohammed, there's a question on Discord. One
yeah.
of our students asked that is edge the same as distributed computing, or is there a difference?
Yes, that's a good question. Yes, Edge is another distributed system. I will refer to this point when we arrive at edge computing. Yeah, but the short answer will be yes, right?
Mhm.
Wearable sensors that are connected to the workers to monitor their health, their psychology, and things like that can be another uh, uh, application of Internet of Things. The site manager could have like a tablet that is running a tracking application to track the situation of the transportation,
Yeah.
or drones could be also another mm, computers that are running IoT applications, right? So we can see that Internet of Things is involved in many different directions of our life, uh, but at the same time that they are evolving, there
Mhm.
are many challenges with them that need to be addressed. For example, let's have a look at this short clip video. I hope it starts. Yes. Is the video's voice sharing?
Yes.
Good. Right. And we can see that it seems the Internet of Things is growing a bit behind our understanding of the Internet of Things. You can see that smart cars have been developed and are ready to use, kind of, but we see that we don't have enough preparation for them. We can see that in this use case, the police are not understanding how to deal with this situation, right? And
Yeah.
even the car doesn't understand how to react to this situation, right? It seems there are very critical challenges with the Internet of Things in terms of changing their rules or uh, being in line with the private sector collaborations, the privacy of the people and the use cases, like when you are using smart home,
Mhm.
then what will happen to the privacy? Education will be another challenge. We need to educate people to properly deal with this Internet of Things and so on. But maybe you would say what kind of the challenges in the Internet of Things are related to us as researchers in computer science or information technology and things like that.
Yeah.
Uh, in that case, I would say one of the main challenges for Internet of Things that can be handled by us is efficient and effective data processing for the Internet of Things that is really needed to be improved. And and I would say maybe the very basic question to ask would be where to process these many IoT applications, right? We will have hundreds of or millions of IoT applications running around us in different use cases. And all of them are producing data to be executed somewhere. So, where should we do this processing for the IoT applications? Maybe the very first answer coming to mind would be, well, we leave the processing to cloud computing that was already there and it is reliable. It's years that we are using cloud computing for many difficult tasks, and cloud computing has like very powerful data centers, and we don't need to worry about that.
Mhm.
Uh, but we at the same time know that Internet of Things applications are a bit different than the other applications we had before because now IoT devices are expected to have generated 73 zettabyte of data by 2025, which is a lot for sending this many data, this volume of data to the cloud, right?
Yeah.
There, there will definitely be a bottleneck to send all this data to the cloud data centers. And also, cloud is not always accessible. For example, if we are going to uh, do the processing for a smart farming application that doesn't have any accessibility to the internet,
Yeah.
how can we rely on the cloud? What's the alternative? This could be like not only smart farming, it could be even IoT use cases in the forest or on the sea, in the ocean, or whenever that we don't have access to the internet. And also, cloud is not always feasible because IoT applications, or at least some of them, are very latency critical, and the very little delay of waiting for the data to be sent to the cloud and be processed and returned back will be very critical, right? So
Yeah.
we need, for example, in this smart car or connected cars, even some few milliseconds are important to us, right? So we don't want to wait for the cloud to process data for us. So considering these uh, particular features of the Internet of Things, it seems we need another computation layer called edge computing,
Yeah.
and we believe edge computing can handle this problem, or at least some of these problems with Internet of Things.
So, Mohammed,
Yeah.
until now, was just a summary that the cloud computing is not always accessible, and if we want to send all the data that is produced to the cloud, would be a bottleneck in terms of network bandwidth. And the third one you mentioned, what is it?
Uh, it's about the latency that
Yeah. Yeah.
will not be tolerable by IoT devices or IoT applications. Right?
Mhm. Thanks.
Yeah. No,
Mhm.
and there could be some other problems with cloud computing, like the privacy. In some use cases, for example,
Yeah.
people don't want to send the data to the cloud because of the privacy, right?
Yeah.
So, yeah, what we know is that it doesn't mean that cloud computing is always a bad solution. No, still
Yeah.
many use cases will be the best to run on cloud computing, and
Yeah.
also some of the edge use cases can use both cloud and edge computing, right?
Yeah. So deep.
But at least we know that what we learn by these limitations, we is that we need edge computing. And why? I will tell you that what will edge computing do for us? Uh, when we say edge computing, we mean a computing layer between the Internet of Things and cloud, right?
Mhm.
And you can see that even in this graph, edge computing is also connected to the cloud, which means it's not that the Internet of Things will always rely on the edge. There is many cases that the edge also needs the cloud, which means if the data is produced by Internet of Things applications and sent to the edge may decide to send the data to the cloud for processing or for storage or anything like that, right?
Mhm.
But we know that edge computing is a critical part of this computation. This it's not always like this three layer. Sometimes people design the computing layer in a four layer fashion. Like you can see at the bottom, we have end devices or users, or let's say Internet of Things applications and devices. Then we have distributed edge. On top of that, we have fog computing.
Mhm.
That is kind of more powerful computers than edge computing and less powerful than the cloud data centers.
Yeah.
But actually, this is just for a reference. In practice, we don't have any. limitation for the number of computing layers, there might be a use case that we just have edge. There might be a use case that we have uh, edge and cloud without fog, right?
Yeah.
And it's just for a reference. If
Yeah.
you do like a survey on the like papers on the uh, edge computing, you can see that people are just
Mm.
defining edge in many different ways. For example, we recently did a project that in the project we merged edge and Internet of Things, and that's it. And we didn't have any fog and cloud, and even uh, uh, edge plus Internet of Things. We had just edge that also is the Internet of Things, right?
Yeah.
And if you, yeah,
Yes, I wanted to say that is nice. Uh, okay, reference that it also shows that when we are at the edge, we have low latency, but and
yeah,
less,
exactly.
and
Yeah,
yeah, yeah,
yeah. By definition, we believe that when we are at the edge,
mm-hmm,
we will run our application with a low latency,
yeah,
and when it goes to the fog and cloud, the latency will be higher because it needs to go through the network to reach that far step and run the application for us and return the response. In terms of capacity, also, uh, by definition, the devices in the Internet of Things and Edge have more capacity for the computation, for the storage, and anything like that. And when we go upper to the cloud and fog, the devices have more capacity. But this is to just get an idea of the differences between different layers of the computation when we have multi layers of the computation. But in practice, we know that these are not always the case. For example, when we say if we run the applications in edge computing, the latency is lower, and
yeah,
when we run the application on the cloud, the latency is higher. It's not always true because, for example, if you have an application that needs uh, like each execution of a task takes, for example, 10 seconds,
yeah,
right?
mm-hmm,
If you run it uh, um, on an edge device, because the edge device has very limited computing power, for example, the edge device could be a Raspberry Pi with like very
less power.
limited, very limited CPU capacity. It will
Mm-hmm,
take around 10 seconds to run a task like an object detection.
mm-hmm,
But uh, if you think that you better run it at the edge instead of sending to the cloud, that's wrong because you can just send it to the cloud and this will be executed in milliseconds,
yeah,
right? So it depends. When we say the latency at the edge is lower than the cloud, or when we say the capacity at the edge is lower than the cloud, it sometimes depends on the application that we are talking about, right?
yeah,
But this is just an overall idea of what we know as cloud, fog, edge, and IoT devices.
yeah. And there is a question here.
Yeah.
One of the students asked, is for computing uh, on, for example, a gateway, or I guess edge is kind of a local data sync. Yeah, he wanna know exactly what.
Yeah,
Yeah,
yeah. Again, we don't have a definition for these things. For example, the Internet of Things uh, devices are producing data, and the data needs to go to a gateway, right?
yeah, mm,
You can consider this gateway at the edge,
mm,
you can consider this gateway on fog computing, or you can consider the gateway on the cloud. So
Yes.
whenever the gateway is, the data would be first delivered to that gateway, and then that gateway decides to where to move this task to be executed, right? We,
Mhm.
by definition, we usually say Internet of Things applications send their data to the edge devices as gateways, and the edge devices decide on whether executing the task locally or offloading the task to the fog or to the cloud or something like that, right? Yeah. This is the
Thank you
uh,
for
yeah
explaining.
the basic of uh, placing the gateway in this system. But there is no limitation. You can definitely convince people that it is better to put the gateway in the cloud for some use cases, right?
And the other question that we are not arriving to this because it's about energy, but some students ask that how do you evaluate if you save more energy by doing the analysis closer to the ESP32 or closer to the cloud? Is a question about uh, yeah, evaluation of the saving more energy.
Yeah, but the problem here is where, like in a broad view of this multi-layer computation, the problem is always where to execute the task,
Yeah.
right? And this will be important because of the energy, because
Mhm.
of the latency, because of the privacy, because of many things.
Mhm.
And each computing layer will affect these parameters differently. Particularly about the energy, uh, we believe that if we run the task on the edge devices, it's more expensive than running the task on the cloud or fog. Because, again, by definition, edge devices are meant to be very limited in their power, and it's very important for us to not consume their energy,
Yes.
right? But we don't have such a problem with cloud computing,
But
right?
still, we have a trade-off because we should send data to the cloud, so it's cost.
Yeah, that's exactly the problem. We always have this problem of trade-off.
Yeah.
If we achieve energy efficiency, it means, for example, in this case, instead of running the applications on the edge, we are sending all of them to the cloud. So it means it is very likely that we are losing the privacy, we are having a longer latency, things like that.
Hmm.
Right. So there is always a trade-off.
Exactly.
Yeah. So when we talk about connecting IoT devices to each other or connecting them to the edge computing, which it means, for example, in the smart farm use case, we enable the fake owls to communicate with each other, right?
Yeah.
For example, I just want to give more details about this fake owl, how it works. This fake owl is running for microservices,
Hmm.
but it's one application, but the application has four microservices. At first, it has a sensor that is like a motion sensor. As long as it sends a motion around the owl, then it triggers the camera. The second microservice is this camera that tries to take a photo of the area.
Hmm.
The third microservice is object detection, that is a machine learning application that tries to search in the photo to see if there is any object like a bird.
Hmm.
And if that's the case, finally, the fourth microservice tries to make an actuation, like making some noise to deter the bird, right? This is an example of making this Internet of Things and edge computing.
And Mohammed, you have done this project in Australia.
Yeah, this is the project that we recently did. We have some fake owls, and also instead of a farm, we use my supervisor's backyard because of this COVID situation.
Yeah.
Yeah, I wasn't there, but the paper is published. I can share it with you later on.
Yeah.
That's a very interesting research project.
Sure.
But something funny about this project was that the birds, after a while, didn't pay any attention to the fake hours, and it actually didn't work very well. But it was just for experiments.
Yeah.
Yeah. Uh, Again, when we say edge computing, if you remember, we had this smart building construction site that there was many applications working. We can bring edge computing in this scenario as well. Like you can see, you can put some tiny servers throughout the construction site
Mm.
to run the applications for us. And when we say edge devices or edge nodes, it's not always a regular computer. It could be like a PC, a drone can be an edge node, a robot can be an edge node, right? So any digital device with a computation power can be called an edge node, right?
Mm-hmm.
That's something very important that makes this area of study very interesting. Uh, Now we have a background on edge computing, and we already know Internet of Things. Maybe a good way of dealing with edge computing would be about energy efficiency and how to deal with energy matters at the edge. Uh, let's get some idea of the energy matters at the edge. When we talk about edge computing and we don't talk about cloud computing, there's a big difference here. And the difference is that in edge computing, the devices are meant to be powered by renewable energy sources. It's not a rule, it's not always the case for all the uh, edge computing scenarios, but it's very critical to deal with this problem because of the global warming problems, because of the limitations that some of the edge computing use cases have, and they cannot be powered by other sources like the grid, right?
Yeah. Mhm.
So it's very critical to deal with edge computing scenarios that they are running on renewable energy. And it could be something like this: some edge devices connected to each other and connected to the Internet of Things applications. The edge nodes are powered, for example, by
Solar panel.
solar panels. Yeah, and they are also running on a battery to store for storage, right?
Yes.
But the problem here is that when we rely on renewable energy, they are always limited, variable, and unevenly distributed, right? You can see that here node 1 is receiving a good amount of energy, but node 3 is dying, right? And it's not just about energy. We know that each edge node will be exposed to a different rate of workload. We don't know. We are not just considering that the temperature thing is producing the same amount of workload as this ambulance one. They are
Yes.
always different. So that makes the problem a bit more complicated, and that's like the nature of renewable energy. It's always variable and you don't know how much energy each device will receive, or at least it's very difficult to understand how much they will receive, right? Uh, this is where some problems are raised in terms of sustainability of edge computing or energy awareness or energy efficiency. We could just use either one and go for that one. What we say like energy efficiency or energy awareness, right? So this problem is raised here, and it's important to deal with that.
Can you give
What?
us this short explanation of sustainability, energy awareness, and energy efficiency, in case that if someone doesn't know?
Yeah, good. Yeah, when we say, for example, energy awareness, energy efficiency, we mean that edge nodes need to be aware of the energy they have, the energy they are consuming, and how long they can survive, right?
Okay. Mhm.
If they don't have this understanding, for example, this node tree is dying, but if this node tree already knew that it is running out of battery and it needs to do something, then it could do something about it, right? Without
Mhm.
just dying and living there,
You
uh,
mean it
this
itself
ambient.
that I am dying? So some kind of
Yeah,
smart,
yeah,
yeah, yeah.
yeah, yeah. This smartness, is missing in terms of energy, right?
Yes.
Uh, so there is this energy problem or energy management problem at the edge.
Mhm.
But the good news is that when we develop an edge computing, it's a distributed system and there is resource sharing available. Edge devices can share their resources together. It's not like this uh, server walks to another server and give them some resources. No, because of the networking, they are enabled with sharing their resources. Uh, and by sharing resources, there are many opportunities for edge computing to improve the energy, to manage the energy, and also in this talk we are just considering energy, but in fact we can use this resource sharing for addressing many other problems in edge computing, not just energy, right? And the opportunities enabled by this resource sharing are known as some techniques that we can use, like computation offloading, task offloading, load balancing, migration, and consolidation, and things like that. Right. So we can use these techniques to benefit from the resource sharing and to address the problems, including the energy. Right.
Yeah.
Uh, to give a better idea of these opportunities, consider this Internet of Things and edge computing. And we know that these edge devices are powered by renewable energy. And in this example, this node tree at the bottom is running out of battery. If resource sharing is enabled in this platform, the node tree can, for example, offload its application to node one that has enough energy.
Yeah.
So the execution of this application from now on is done on another node. And this node tree can save some energy because one of the main reasons edge nodes lose their energy is doing some computation, some processing, right? So by offloading their application on another one, they can just offload the computation. Another solution would be instead of moving the application, just moving the tasks that are produced by the IoT devices to another device, right? This one is called task offloading. And we can also call it load balancing if you want. Another technique we can use is to just turn off some devices, some edge devices that are not working very efficiently. For example, they are not having um, many requests, or you can see that you can just ask other edge nodes to handle their work, and
Yeah.
they can just be turned off. And this is called server consolidation. This is important because research shows that an important portion of the energy on the nodes are just consumed while they are idle, right? So
Yes.
we can just turn them off and save the energy for uh, for later, right?
Yeah.
So this is how we use the opportunities of resource sharing at the edge and different techniques we can use. There are many other techniques that people can use uh, to benefit from the resource sharing at the edge. And if, for example, we want to implement that smart solution that is going to uh, dynamically make decisions about where to put the applications, where to put the task, where to turn off the servers. We need something like a scheduler in our system.
Yeah.
For example, in this
Scheduler,
example,
a scheduler decides where and when a task should be executed.
yeah, exactly.
Mhm.
Yeah. So, for example, in this scenario, the scheduler, when faces this problem that node A is dying, node C is full of energy, and node B is so. To save node A, it may decides that I will A upload your application to our C,
Mhm.
right?
Yeah.
So this is what the scheduler will do if we have a smart scheduler, or we have a scheduler that is aware of energy, right?
Yeah.
And it's a bit tricky now because, for example, here, our C will say, I cannot handle ours A application. And we know that each application in this case has 4 microservices.
Mhm.
Our C means that it's 4 microservices. I cannot handle all of them, right? Because of, for example, this owl C can run two other applications or two other microservices, not 4, right? So what can we do now? Because we know that monolithic applications cannot be divided into different parts. So we can just move two parts of the application somewhere else
Yeah.
and run two of them locally, right? This is the
Yes.
problem with the deployment of applications, which means the application deployments need some changes.
Mhm.
They need to be portable, right? Yeah, right. So what can we do with the application deployment problem, right? We just want to uh, branch to serverless computing to deal with this deployment problem, and then we get back again to the energy, right? We know that when we have monolithic applications, it means we have an application that we just need to see the application as a whole. If it has 10 microservices, or if it does 100 different tasks, all of them are seen as a whole. If you want to move this application somewhere else, if your scheduler has told you that you need to move this application somewhere else, you should have enough capacity for this application in the remote host, which means you need to have capacity for 100 microservices of this application, right?
Mhm.
Because it's monolithic.
Yeah.
But with a better design of your application deployment, you can go for microservices. That means you can divide your application into different pieces, they can work separately, and still there is a bit of dependency between microservices in some cases, but it's very easier to take them apart, right? This like this deployment problem leaves us to the serverless computing. It's a few years that serverless computing has been introduced as a new model of application programming and also deployment.
Uh,
Serverless, yeah,
Before we go to serviceless computing, I have a question in the
yeah.
previous slide. Um, do we write our application in a microservices way, and in that case, it can be divided to, to the to some services, or is it us that we decide how to write our application, because the monolithic applications cannot be divided, so we should write them in a microservices way, if I am.
Yeah, like it's always a hassle to turn a monolithic application into microservices
Mhm.
architecture, right?
Yes.
If you are like the best practice is that if you are developing a new application, it's better to start with a microservices architecture.
Yeah.
But if we already have developed our application and it's monolithic, that's itself a very important research area. Many people are working on how to do this transition from monolithic application to microservices,
Yeah.
and it's a bit a hassle if, especially if the application is a big application and it has many dependencies between different services. And also it's good to refer to this point that it's not always the best to move from monolithic to microservices. Sometimes, in some use cases, we have to stay with monolithic architecture, and it gives us a better performance. I don't know many examples of them, but like there should be some examples. Although we know that many applications are better to be microservices based, right?
Mhm.
Yeah.
Yeah.
So
There is another question.
yeah,
Uh, is a microservice kind of its own thread in some kind of parallel programming?
uh, it could be another thread, but to better split your application in microservices, I would say you have uh, instead of one application that all its components are connected to each other,
Yeah.
you have some applications, some small applications that each of them can be seen as an application, but they are able to live independently. And at the same time, as they need to communicate with each other, we have APIs, and there are many solutions to resolve this communication between applications, right?
Yeah.
Yes, but still, when we are dealing with microservices, we are just one step after monolithic, which means instead of one chunk of big application, we have uh, a few or a lot of small applications that have some dependencies together, but because of the APIs and the communications that are resolved, they are okay with these dependencies.
Yeah.
If we want to go for a more modern way of application design, we should go for serverless. computing that gives us function as a service. So instead of microservices, here we have functions. The big difference between functions and microservices is that functions have zero dependency to other ones. They just live by themselves. They can survive without needing any other application or microservice, right? So it means if we move from monolithic to microservices and we remove any connection between microservices, then they are functions.
Okay. So
Let's say.
function is the finest grain.
Yeah, the finest grain, and it also has some other additional features that make function different than microservices. Like functions in serverless computing are stateless, right? So, for example, the storage is decoupled from the application, while we didn't have to do that for microservices, right? Uh, Maybe you ask, what's this serverless and functional service? Let's give a demonstration on how we achieve serverless function or functional service, right?
Yeah.
Assume we have an application running on our system. We are, for example, running Paint or a video player or something on our on our system. It's running on the OS. It's consuming CPU, RAM, and storage as much as it wants, and there is no limitation on that. And it also may have some dependencies that are installed on our system, and our OS is handling that, right? And if you want to move, for example, this application somewhere else, it's very difficult because it needs to understand how to resolve the dependencies on the OS, on the runtime, and things like that. And it's not very efficient to run applications like this because, for example, one application can consume all the CPUs on the system, right?
Yeah.
Instead, with serverless, we mean a platform that is installed on our server.
Mhm.
This platform gives you a template to deploy your application, which means it gives you function as a service. Function as a service is like instead of uh, instead of running or instead of programming your application uh, as a whole, you just pick one functionality of your application and write the code inside a template that the serverless platform will give you. Like if you are using AWS Lambda, it will give you a template and you just put your code inside that. If you are using like an open source serverless platform, it will give you a template and you just put your coding inside that. And you don't have a limitation on the programming languages. You can use any language you want as long as the serverless platform supports, and they usually support many languages. When you write your code and give it to the serverless platform, it will containerize your function for you, which means it will build a container out of your function. It could be like a Docker container, right? And also, it will make the container stateless. It will remove the storage. You cannot store anything in the function. If it needs a state or data, it's not the thing with serverless functions, right? And when you run your function and send requests or tasks to the function, this serverless platform is monitoring the load on your function, and if it needs, launch new replicas of the function for you. And if the load is going down, it removes the replicas depending on the workload, right? So you can see that the only thing with this new model of deployment you have to do is just writing your code. And the rest of this, all of that is handled by the serverless platform. And this is why they call it serverless, because you don't care about the server. You just care about the coding and programming and all the server things like running the application, managing the application, auto scaling, all of the things that are done by servers are hidden from you, right?
Yeah.
So when they say serverless, it doesn't mean that there is no server at all. There is server for running your application, but
The
it's not
responsibility.
your responsibility to handle that. Yeah.
Hmm. And
Yeah. Yeah.
what are I mean, the platforms that are provided, some.
Yeah, the very first serverless idea was by Amazon. AWS Lambda is the service in Amazon that provides this function as a service for us. And then other IT companies like Google, Microsoft,
Oh,
IBM, Oracle, all of them joined this industry, and all of them are now providing this function as a service. And also, there are some open source solutions. You can use them. I am personally using OpenFast,
okay.
which is an open source serverless platform. There are other ones like OpenWhisk, Kubeless, and things like that. And all of them do the same functionality for you. You install them on your server or the cluster of servers. Then you can write your functions and give your functions to the platform. The platform will deploy your application, give you an endpoint to access the function, and then you are done. And everything is handled by the serverless platform. The only thing you have is just an endpoint to access your function, right?
Mhm.
Uh, and the functions are also stateless,
Mhm.
which means uh, they don't have the concept of storage, for example. And if you need storage, it is decoupled from the function. You can have like a database somewhere else to store the data that you need for the functions, and the functions can just read and write to that database instead of each of them having a database for themselves. Right?
Yeah, okay.
Yeah. So with introducing serverless, if you remember, we were in edge computing and we were talking about green and energy efficiency, and we reached the point that uh, we know that a scheduler can be very helpful to handle the energy matters at the edge, but we stopped at one point that we cannot properly move the applications around based on the scheduler decision. And now with this understanding of serverless, we can see that we can actually um, divide our application into different stateless functions
Mhm.
that can be just moved around because they are small pieces of the application. They don't need that much capacity, and also they are stateless. So it doesn't matter if you run a function on server A or server B or server C because it doesn't have any dependency on storage, for example, right? So it could be easily moved around. So I think serverless functions are of the best material for doing this scheduling in edge computing. And this is why we started working on serverless at the edge, right? For example, in this example, if you remember, this node A was told by the scheduler that move your application to node C, and node C didn't accept that because it says, I don't have that much capacity for accepting 4 microservices of this application, right?
Yeah.
Now with serverless, we the scheduler decision will be, our A, move function 3, which is the object detection, to our C, right? This function 3 is like the most computational intensive task of this application. This is where we consume lots of energy. So this one is better to go to node C that has good capacity for energy, right? And
Yes.
then also function 2, which is the camera handler, and can be handled by our B, right? So you can see that when we have functions instead of applications, it's very easy to decide on the scheduling
Mm-hmm.
and also deal with the limited capacity of the nodes, right? Because we know that edge nodes have very limited capacity in terms of like CPU, storage, RAM, and things like that. And if we don't have this fine-grained deployment of applications, then we cannot benefit that much from this resource sharing enabled in edge computing, right? This is one of the reasons I believe serverless can really be very helpful for edge computing,
Yeah.
right?
But how much it is finer? I mean, we go um, finer from applications to functions, so more metadata, which is store and know about. Um, or
So you mean it will have like overhead or?
yes, exactly.
Yeah, yeah, that's one thing. That's a challenge with serverless platforms because, for example, if you uh, for this smart farm in our project, we use an open source serverless platform, right? And serverless platforms normally are running on container orchestrator tools like Kubernetes, right?
Yes.
So we needed to, first of all, run Kubernetes, although we use the light version of Kubernetes, still it's consuming a considerable amount of RAM on the nodes. Then we installed the serverless platform OpenFast. And for example, if we have 1 gigabyte of RAM on a Raspberry Pi, by just installing Kubernetes and OpenFast, we are consuming something around 400 or 500 megabyte of data, right? So this is a big overhead, right?
Yeah. Mhm.
We tried that. We tried to achieve that to just do some experiments to demonstrate that serverless is giving some benefits. For
Mhm.
example, for this fine grained scheduling, right? But we acknowledge that it has some overhead and people can work on it. Like people can work on how to develop a serverless platform that doesn't need Kubernetes,
Yeah.
right? How to
Mhm.
develop a service platform that is lightweight enough for edge computing, right? And that's a very interesting area of research, and I am very interested to go for that.
Mhm.
Right.
Yes.
Yeah, so serverless at the edge was one of the very first uh, problems we deal with in my PhD. We invited some experts in this area, some experts on serverless, some people on edge computing, and we had a very good discussion on how to bring serverless to the edge. What are the challenges of serverless at the edge? And the point you mentioned was one of them also. It has overhead. How can we handle this overhead? And finally, we achieved a taxonomy of the opportunities that serverless will give us at the edge and the open issues that serverless needs to address before coming to the edge, right?
Mhm.
Uh, this paper is published and it receives the Best Paper Award from the Auspidity Conference. It is online now. You may be able to find it. It's called Serverless Edge Computing Vision and Challenges. I'm just going
Yeah.
to quickly refer to some of the opportunities and open issues. For example, one of the opportunities with serverless is that it's a pure pay-per-use pricing model. For example, if you are using the serverless provided by cloud uh, providers like Lambda, AWS Lambda, you are just paying for the time you are sending a request to your function. If your
Mhm.
function is idle, you are not paying for that, right? This is why we call it pure pay-per-use,
Okay.
because cloud computing services are already known as pay-per-use. But this one is pure because you don't have to pay if you are not using your function, right? Because when you are not using your function, the serverless platform will scale your function to zero, which is like a new feature coming with serverless. We didn't have such a thing before.
Yeah. Okay.
Then this always on problem in applications is mitigated, which means this is related to the scale to zero feature of serverless, which means if you use serverless at the edge and you have applications, IoT applications that sometimes are running and sometimes are just idle, in a serverless platform, these applications will be shut down when they are idle. And for example, the containers for the function will be terminated. So in that time, you have more capacity to be used by other functions
Okay.
and other applications. So uh, you don't have this traditional always on applications with serverless.
Yeah.
And
Yes, I wanted to ask, rather than energy management, what other challenges are? You are talking
y-
now. Open.
yeah, yeah,
Mhm.
like that's a good question because I am my research is a bit focused on energy matters,
Yeah.
and this presentation is like serverless or edge computing are just good for handling the energy.
Yeah.
But uh, reality is that there are many other areas of research that people can work on, and they could also give uh, enough benefit. For example, this serverless computing, uh, we can just use it in the cloud, right? We can just use it in the cloud and benefit from, for example, the parallelism that is enabled with this serverless computing, right? So, for example, when we have stateless functions, it means you can run 10 or 100 or 1,000 of them at the same time, and you can just uh, uh, run them in parallel, and you can achieve better response time for your application. It doesn't matter if your application is an Internet of Things application or it's just a regular application you use to use the cloud, right?
Yeah.
Uh, I think this taxonomy gives a lot of new ideas of using serverless, and this paper has received a lot of attention recently, and people just like it. I think
Nice.
you, yeah, I think we can talk about any of these opportunities and open issues for ages. Uh, but I think the best reference would be the paper,
Yeah.
right? Uh, there, I'm just going to quickly refer to some of the issues with serverless, because serverless is not like the the magical thing that we were looking for ages. It has also some issues. One of the issues that is very uh, bold for serverless is the cold start. We know that in the distributed systems, always we have this trade-off. This cold start is coming from the uh, the point that serverless
Mm-hmm.
turns off the function when the function is idle to save energy, to save resources, and so on, right?
Yeah.
But when we send a request after a while to a function that is turned off, it takes a bit of time to return the function back
Mm-hmm.
because it needs to run a container. It needs to run the runtime inside the container and run the application inside the container, and then it will be ready to process this request, right? So there will be this process is called cold start,
Mm-hmm.
right?
Yeah.
And this is not like a few minutes. It's normally a few milliseconds, or if your function is very heavy, for example, it needs to load some machine learning data and things like that, it could be maybe a few seconds, right?
Yeah.
Many people are working on fixing this problem of cold start. But when you start learning about serverless and you start understanding the challenges with serverless, you will definitely be faced with this cold start at the beginning, right? Vendor locking is another one because if you want to use cloud uh, serverless services like Amazon, uh, there is always this vendor locking problem. Energy agnostic is another issue with serverless because when it comes to scheduling functions, putting functions on the edge nodes, usually the serverless platforms and even the container orchestration tools don't know about energy and don't care about energy because they are basically designed for uh, uh, cloud and environments that are not limited in energy. This is an open issue that we are also working on in my PhD project,
Mm-hmm.
and there are some other ones, right? So far we have learned about Internet of Things. Edge computing came to handle the Internet of Things. Then we understood that serverless can help edge computing to achieve its goal, right?
Yeah.
And we know that scheduling, especially the scheduling that is based on energy awareness, uh, is a problem to be addressed. Uh, this is not the only problem. There are hundreds of problems when it comes to scheduling, energy awareness, and things like that at the edge for IoT applications. Here, I just want to show you a sample problem that we addressed by developing an energy aware scheduler, right? To see how we uh, do a project based on the theory that we learned in this area, right? Uh, our uh, evaluations and our implementations are based on this use case, smart farm, right? We set up a cluster of Raspberry Pis that are single board computers. We use Raspberry Pi 3 for the 5 nodes and Raspberry Pi 4 for a controller. The difference is in their CPU and memory capacity, basically. Right? The Raspberry Pi 4 is a bit more powerful. Because of that, we use that as a controller that runs some scheduler and things like that.
Mm-hmm.
Then we connected a battery to if to edge nodes. The PiJuice battery is used, which is the original battery for Raspberry Pis to store some energy. We For energy input, they are meant to be connected to solar panels, right? But for the sake of our experiments, we just used some renewable energy data,
Mm-hmm.
and based on that, we gave energy to the edge nodes in a different rate. We can see that in this chart, each node is receiving a different energy input. This is an experiment for 24 hours, right? Then as we are going to use serverless for the deployment of our applications, we need to enable containerization. So we enable Docker on the edge nodes, and to install the to install the serverless platform, we need an orchestration tool, container orchestration tool. So we use Kubernetes K3s, the light version of Kubernetes. And on top of that, we use OpenFast as the serverless platform. And because our applications sometimes need to save data somewhere, we also use a database, and our database is Redis. We can see that the gateway is on the controller, and all the nodes can be connected to the controller using this gateway, right? And this Pi agent, this green box, is what we actually developed. Before that, all of them were actually just using available technologies. This Pi agent is the scheduler we developed. This is a Python code of like 4,000 or 5,000 lines that defines the scheduler. It has a scheduler that is continuously monitoring the energy on these edge nodes, for example, every 10 seconds. And every, for example, 5 minutes or 10 minutes, it's making a decision about where to place the functions. Like each node is running some applications, and for that application, it has some functions because we are using serverless. But they will have different battery charge at the time, right? So this scheduler is watching them, and if the scheduler sees that, for example, node 1 is running out of battery, it decides to offload the functions of node 1 to other ones, right?
Yeah.
In this way, node 1 can survive longer. Hopefully, after a while, it can receive enough energy and it can get its functions back. And the application running on these nodes are this object detection, and which is like a YOLO object detection. YOLO is like a framework for machine learning use. And when we run the experiment, in fact, we randomly send requests to the applications running on the nodes. Each node is receiving a different rate of workload. And this will go for 24 hours. And the scheduler will, every 10 minutes, I think, make a decision about the placement of functions. And this is how this scheduler can handle the variability in energy input and also in the workload, right? By this, we automated this process, and this is the setup we finally have: some Raspberry Pis and some USB power meters. And and if I want to give it more details of the scheduler, how the scheduler makes decisions, it was kind of matching. Every time it has some functions, each function has some size, some considerations, like some of them need to be more private, need to stay locally. Some of them don't need privacy thing, it can be anywhere. And on the other side, we have nodes with different battery charge, with different computation capacity. And this is like a matching problem. And we solve this matching problem every time by using a mechanism called "you request my house, I get your turn." It's called a house allocation with existing tenants. Assume we have 3 functions: function 1, 2, 3, and each function has a preference to node D1, D2, and D3, right? For example, we can see that function 1 has the highest preference to D2. And then if it couldn't receive D2, it is happy to be placed on D1. And
Yeah.
finally, if neither of them were available, it could happy to be on D3. And the same for other functions. We start with finding a place for function one. One requires node D2. So D2 has some functions that are not already placed somewhere. Like when we say D2, it means F2 belongs to D2, right? So function one goes to a cycle, then functions of D2 come up and they start deciding for searching for a place. F2 wants D1, for example, and we can see that D1 belongs to F1, and this is
Mhm.
like a cycle that goes until a cycle happens in their request, and then everyone receives what they want, and the cycle is clear, right? And finally, F3 is left, and F3 can just get D3, right? Uh, there are more details about this algorithm. The paper for this one is not still published, but I
Yes,
am hoping that this one gets published quickly.
Mhm.
By this strategy and this energy aware scheduler, we could save up to, or we couldn't save, we actually uh, made the energy uh, uh, 40% more balanced in the cluster, right?
Mhm.
Right. So to summarize this presentation, we know that Internet of Things is evolving at a fast rate, and
Yeah. Uh,
yeah, and yeah,
since I just um, come up with this question
um,
that if the hardwares are heterogeneous in IoT, so how software developers deal with this developing this heterogeneity? I mean,
yeah, yeah, yeah. I see. That's kind of like the very big differences between what we did in the cloud and what we have in edge computing. Like uh, a few years ago, we used to do scheduling, energy efficiency, and things like that for the cloud. And we always did have this problem that the cloud data centers or virtual machines we are working on and evaluating will have different architecture,
yeah,
hardware architecture, for example. Now we have uh, AMD, we have ARM architecture, and so on, right? And this is very relevant to the edge not cloud based on the research we are doing. Which means in an edge scenario, when you uh, are making a cluster of edge nodes, it's very likely that you have edge nodes that are running on an AMD, for example, or Intel architecture, or some of them are running on an ARM CPU architecture. Some of them may have very limited uh, CPU capacity. Some of them may be powerful enough. Some of them may run Mac OS. Some of them may
mhm,
Linux. Some of them may run Android. Some of them may have internet access. Some of them may not have internet access. Right. So this heterogeneity is in edge computing, and that's a big challenge to be addressed. Right. We need to propose solutions that can handle this heterogeneity. Otherwise, um, our solutions will not be practical, right? For example,
yeah,
if I want to propose a scheduler, if I want to propose a load balancer, if I want to propose a task offloader, it needs to understand the difference between the edge devices, right? Yeah. So in this talk, we had a basic idea of Internet of Things and how edge computing is as a distributed system. to handle this. We talk about energy efficiency as a major challenge for edge computing, among others.
Yeah.
Energy efficiency is not the only matter when we talk about edge computing. And I just highlighted energy efficiency because this is my research and my area of research. There are many other problems and challenges with edge computing. And then we introduced serverless computing as a great facilitator for addressing edge and energy problems. But we know that energy is not the only problem that serverless can be useful for. There
Mhm.
are many other benefits with serverless. And with such emerging technologies, now what we can do is that we can go for making some optimizations for edge computing, just designing an edge cluster and
Mhm.
trying to optimize the scheduler, the load balancer, the OS, the application deployment, programming, and anything about that. Right? Thank you for your
Thank,
time and being patient with me.
thank you so much, Muhammad, for nice topic today. I hope a student enjoyed it and
Thank you.
they can apply it in their thesis or in the courses they take. So should say goodbye, and we will see. I mean, a student each other to the next lecture that is held at 3 p.m. Good morning and thank you. Sorry, goodbye and thank you so much.
Yeah, it's actually 10:30 p.m. in here.
Yeah, 3 p.m. at student
Yeah,
time.
that's good. It's good to be with you. If there is not any question, I have to say goodbye.
Yeah. I don't see any question, and I have no question since I asked a lot of question while you were presenting. Thank you so much.
Yeah, that's okay. Yeah, if anyone has a question later on, I am available on LinkedIn always, and also ResearchGate, and my email address is also here. Just feel free to ask me any question you have.
Yeah.
Okay, thank you.
Thank you.
Bye.